Hello, welcome to Engineers Ireland. Today we're going to look at probability and counting. This particular section is one that seems to give headaches to a lot of people. Perhaps the reason for it is it's one of those sections where you really have to be very precise, very careful. Now, the ways I like to put it across is more through the language of it rather than the mathematics of it. There are certain keywords, and if you get careful with the use of those keywords, I think it becomes much easier. So let's see if that works for you guys. Well, the first rule of counting relates to one of these. First fundamental principle of counting. And it's the first opportunity for you to see the connection between a word and a particular mathematical operator. So, what this says, if we have to perform a test and another test, you've already got the keyword, and the keyword is and. So some test and another test. When you get that word and, it'll mean multiply. So then, if the number of outcomes of the first test is x, the outcomes of the second test is y, then the total number of outcomes so outcomes of the first test and so and means multiply. If we have a six-sided dice, there's 6 possible outcomes. Assume the sides are numbered from 1 to 6. There's the 6 outcomes. It could be a 1, 2, blah, 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 up to 6. Tossing a coin, 2 possible outcomes, a head or a tail. The total number of possible outcomes under those circumstances is outcomes from dice and six possible outcomes from the dice, 2 possible outcomes from the coin, totals 12. The principle has been shown to you by just using 2 tests. This will apply to any number of tests. And a simple example can be provided of that. The second example in Rowntree's book has a serial number consists of a letter followed by 3 different digits. Okay? That's an important word. You'll recognize as we go through this chapter that words are very significant here. So we're now talking about, there'll be one letter. It's going to be 3 numbers. What's the important thing here? They're different numbers. Okay. 26 letters in the English alphabet. So there's 26 choices. So we're getting a letter, and we're now going to pick a number. And we'll pick a second number. And we'll pick a third number. So we've set out what we wish to do here. And the easiest thing is to not think in terms of the ands or other words such as that at the moment. Just look at the individual little tasks, the elements that are in here, the particular tests that are being applied. That's generally the word to this. So 26 possibilities for the letter. Now, digits. 0 up to 9. That's 10 digits. So I have 10 possibilities for my first one. Now, just because we have taken one out there, it means for the second number, it's only 9 possibilities. Because remember, our numbers, we were told, were different numbers. And if that's the case, having 2 numbers used out of the 10 possible digits, for the third one, we only have 8. Now we look at the effect of the ands. And means multiply. If you can understand this, then you'll have no difficulty at all understanding the second rule. First rule is something and a second thing. The and means multiply. So let's have a look. Rule 2. So the setup is almost the same. We have X possible outcomes in the first test and Y from the second test. So what makes this different? Well, if it isn't possible for both of these to occur, if it's possible for one to occur or the other to occur, the operative word here is or. Okay? So that's the second thing to remember, that or will mean plus. So the something and something means multiply. Something or something means add. What type of problems does this belong to? A bag contains 9 discs from 1 across to 9. So there's going to be 9 of these items. And a disc is drawn at random and not replaced. Okay? That's the first test. A disc is going to get drawn. Now then, if the number that has been drawn is odd, a second disc is drawn from the bag. But if the initial number drawn is even, then a coin is tossed. So you can see how there are differences here from the original simple little problem that we looked at. So the question is, how many possible outcomes are there? So let's look at it. First, odd. If that happens, we will also be doing something else. So it will be that and second disc gets drawn. So that's the first half of the thing. If we've drawn a disc and the number on it is odd, we will then proceed and pull a second disc. We were also told, but if the initial number drawn is even, so we're now saying, if that was odd, we'll pull a second disc. The other option is or, okay? If the first is even, what do? We then toss a coin. We'll get an even number and toss a coin. And I'll turn that into a big hand for you. That's the game we've been asked to play. So how many odd numbers are there from 1 to 9 inclusive? There are 5 of them. So what's the possibility here? 5 possible odd numbers. Once we've pulled one of the 9 discs, there are 8 remaining. So pulling a second disc is 8 possibilities. We forget the operative words at the moment, we just look at the little bits. If we look over here now, if the first one was even, how many choices were there for an even number? There was 4 out of the 9. And to toss a coin, there's only 2 choices, heads or tails. Now then, we look at our important words. The R means plus. This is an easy game to play. But it's really important because we're setting ourselves up for more interesting mathematics later on in this chapter. But if you get this particular part of it, where you can just recognize that careful usage of words means that and will always imply multiply, or will always imply plus. So we can happily proceed from that, and let's look at a more complicated problem. We're looking for a whole number that's between 100 and 999. Okay? So it's in that range. What's the little game that's going to get played now? How can we add to what we know in a fashion that will allow us build up our information? Sometimes we're forced into part of the game we're playing is a forced part. And the rule in relation to this is if a restriction is imposed, before you think of anything else, you deal with the restriction, you bring in the restriction. So then, what's the restrictions going to be asked of us here? It's one of the digits is 6. Okay? So we're going to make a number in that range. Now that obviously means there's going to be 3 parts to it. First, second, and a third number. So getting a 6. You could have a 6 here. You could have got a 6 here. You could have got a 6 over here. How do we word this? In the first position, you could have got a 6. Or, in the second position, you could have got a 6. Or, in the third position, you could have got a 6. So, the R's now are going to imply pluses to us. So each of these particular situations, the 6 being first, we will look at that. Then we look at the 6 being second, then the 6 being third. The other thing we're told is the 3 digits are different. That's the same as saying once we've used a digit, we don't put back that number into the pile again that we're picking from. So, the other thing we know is if in the first position, if we had 0 in here, well, now our number is not between 100 and 999. So that's something that's not allowed to us. That would interfere in this condition and in this one here. If there's a 6 in the beginning, we don't need to worry about it. With a 0 in the beginning, not a chance, because you're outside the range. Let's look at what we have then. Six in the first position. How many possible ways is there pulling a 6 from the 10 digits 0 to 9? There's just one way. You only can get 6 by pulling the 6. There's only one possibility. So let's look at this. We can set up a little table for ourselves. And we look at what are the controlling commands going to be in between. Okay. Only one option, only one possibility will give a 6 in the first place, and that is pulling the 6 one. Now, again, if we look at the 6 in the second position, here underneath the second one, running down to here, there's just one possibility of that also. And if we run down here, for For 6 in the third, there's only one possibility of that. We have now looked at the restriction. We've imposed the restriction on what we are dealing with. Now, let's start looking at the other bits. The 6 does not get returned to the pile of 10 digits. So, I have 9 ways of filling the second one here when 6 is first. Whatever number I get there, it doesn't go back into the pile, so there's 8 ways for the third one. So we're happy we have the 6 in the first one filled out. 1 possibility in the first, 9 in the second, 8 in the next one. Now, let's get down to this one here, where 6 is in the second position. See it over here? How many possibilities do we have in the first one? It can't be a 6, and it can't be 0. So there's 8 possibilities here. Now, when we're looking at the third location, whatever went into the first is gone, and the 6 is gone. So of the 10, there's still 8 possibilities left. With a 6 in the last position here for the third one, with a 6 just over here, what do we have? Again, there's 8 possibilities for the first position. There's 8 possibilities because it can't be a 6 and it can't be a 0. For the middle position, whatever was put in the first position and the 6 are not possible, so we're left with 8. So that's the numbers bit. But how is the game played? Over here, on the right-hand side, we already know how to look at the 3 different possibilities, 6 first, 6 second, 6 third. And what it basically is whatever answers I get from the top here, it's going to be that or, and again down here. So let's see. For 1 for the first, what are we referring to now? And. How much for the second? And how much for the third? Even on the second row, 8 possibilities in the first, and meaning multiply 1 possibility in the second, and meaning multiply 8 possibilities at the end. And likewise, for 6 in the third position, there's 8 possibilities in the beginning, and 8 possibilities for the second, and only 1 possibility at the end. So that's our table worked out. We can say that what we have is 1 by 9 by 8 plus 8 by 1 by 8 plus 200 possible ways of getting a number, a 3-digit number, where the first digit is not 0 and where we're forced to have a 6. That should be, along with you doing the exercises, of course, that comes into that section, that should be enough on just the difference between the usage of the word and the usage of the word or. The next part of this chapter, which is the bulk of the chapter, relates to 3 different but relatively similar sets of concepts. The first 2 are variations on one thing. They have to do with arrangements. There are key words related to arrangements. One of them is pretty obvious. Okay. Now then, if I go down here, combine, there are keywords. This upper one splits into two parts. The first one has to do with all objects. The second one has to do with some objects. And likewise, down in the combination side of things, it has to do with some objects. Okay, what does the all and the some relate to? If there are a total of n objects in, we'll say, possibilities, what we're basically saying is we're going to start looking at arranging all of those n. Okay? So this is an n problem. If we only wanted to arrange or pick some of those n objects, we will talk about r of them. And this down here is going to be r, again, of n objects. One last little thing. If we are picking or arranging r objects, the amount that we're not arranging is n minus r. And likewise down in the bottom one. I know I'm going to have to clear the screen now so that we can continue, but this screen really lays out the important keywords along with the words you have already, which are and or. Arrange and pick. If you hear those words, you're going to be dealing with this side of things. If it's all, that'll be the first thing we're going to start looking at. If it's going to be some of the n objects, just r of them, saying that many of them, then we'll be just dealing with some objects, and combinations is choose or select, okay? And it's always choose some of the n objects. Let's see how it works. Picking the wrong set there. What's an arrangement? In objects. can we arrange those? So let's look at them. We'd say, let's leave A first, we leave B second, and well, that's forced on us, isn't it? C is left here. Say, okay, there's nothing else I can do here, so let's leave the A first, and now we'll swap these two. And we're saying, while I'm leaving the A first, there's nothing more I can do at the back here. It's either BC or CB. So now I'll say, let's put B first, and we'll go AC. So then BC. With the B at the beginning, there's really nothing else we can do here. Let's put C first. That's 6 possible ways of arranging these 3 items. And there really isn't any other way. The trouble is, we aren't normally asked about 3 items. We can be asked about, it could be 40 or 100 items. And the number of possible ways becomes very prohibitive to work out manually. So then, is there something that we can do that'll help us in this? The handiest thing would be to go back to the kind of way we've looked at things before. And we're saying, what's the particular game we want to play here? We want to pick a first one. And, don't we, want to pick a second one. And we want to pick a third. While we have the 3 letters A, B, C, I have 3 ways of picking the first one. Now that one has been picked, there's 2 ways to pick the second one. 2 possibilities. That leaves just one for the last one. And what we have now is 3 multiplied by 2 multiplied by 1, which is equal to 6. You can clearly see that if we had 4 letters, is what we're working on now. It's the first of the 3 categories that we discussed a few minutes ago. We're picking all within objects. Here it was 3 objects. In picking them all, there's 3 there that you could pick for the first. There's just 2 there that you can pick for the second, and there's only 1 remaining one here. So you can see we're picking all. We're going right down to the very last one. So if we have n objects, what do we have? You'll say first, and pick a second, and pick a third, second last, and last. We're going to pick the whole lot of them, all of these in objects. So then, there's n objects. There's n possible ones for the beginning. The next one is n minus 1. Now it's n minus 2. It's n minus 1 here because we've already picked one away. N minus 2 because there's 2 gone. And we go all the way down. The second last one, there's only 2 of them. There's only one last one. So the little game we played up here shows that from the total number we had, we keep dropping 1 until we reach down to the last item. What we're dealing with here, this set down here, this n by n minus 1 by n minus 2, all the way down by 3, by 2, by 1. We give a name to it, and it's much easier when you have a short name for something than writing a big long thing like that and having to repeat it all of the time. That's how it's written, and it's called n factorial. So, what we've learned is that if we are picking all items, the number of possible outcomes is n factorial. Now then, what if we weren't going to pick them all, if we were going to pick some items? And as I said to you, the other possible way of talking about this, pick some. So we're going to arrange some. The other term that you can see means the same thing as to pick some. That's not all. We're going to be picking R of the n items. If we had 8 items, and we want to pick 3 items. For the first, we're going to pick the first, and then we're going to pick the second, and then we pick the third. In picking the first one, we've got 8 possibilities. To pick the second one, we have 7 possibilities, and to pick the third one, we have 6. There's 336 ways. So this is picking some items. What you will notice is that it starts off the same as picking all. Right? The numbers are dropping one at a time. They're all getting multiplied. But it stops short because it only goes R into it. Now we could have said, isn't that the same as writing this? Because we do see that these things cancel. All n is 8. Number picked which is r, is 3. Number remaining, which happens to be n minus r, in this case, and this, interestingly enough, is the key one. It's the one that tells us what we need to know. Because while we're dealing with this short set here, yes, it's easy to multiply out, but from the viewpoint of getting a general equation, it isn't really useful. This thing here gives us a better insight into it. Now, what are we going to get from this? It seems that when 8 is the n, and the 3 here is our r, what we have n factorial divided by n minus r factorial. That's what we have written up here. We have n factorial divided by n minus r factorial. So what's the nice handy way of remembering the equation? It's normally written this. Now, I normally read that as n pick r, but obviously it doesn't mean pick. How many ways have we of, how many permutations, possibilities do we have of doing our particular job? And we're saying, well, that is n factorial divided by n minus r factorial. And in English, what we can say this time, it's equal to factorial of all divided by factorial of remainder. So NPR equals the factorial of all the items divided by factorial of the remaining items. You can see clearly how it's related to picking all. So picking some, even in the English language, the ways we're speaking about this, relates now back, because if we had picked them all, this would have been the answer. Factorial of them all. When we pick just some of them, how many have you got left? Because the factorial of all divided by a factorial that's left over, that haven't been picked, is the total number of possibilities that we have. This is an example from the book. So there's 7 letters in that word, couples. And the question is, how many? How many 5-letter? Keyword here is arrangements. Remember, we're looking at arrangements. We're looking at picking, or how many permutations. They're the key words in this area of things. So how many of these 5 are possible? We know 7 is the n. how many 5-letter combinations, or sorry, 5-letter items can be made from the 7. And it's going to be factorial 7 divided by the factorial of how many is left over. Now then, it's very, very easy to see how we can combine in other rules that we have. Do you remember we discussed restrictions? If we're now asked to bring in a restriction, and the restriction is that the O must be last, that this must be one of them, and it must be the last one. What you can see in this second question is of these 5 that we're going to look at, we're forced now to shove an O in here. There's only one possibility with that. So we're really now looking at all of these. And we're saying, there's 4. I'm going to have to pick 4 now. And if you go back up to the word here, the 7 letters in it, but the O has been forced in at the last position. So there's only 6 now that we can pick from. We're going to pick 4 from 6. So this time, what we have is 6P4. Big difference, isn't there? When one of the letters is forced and its position is actually forced, we've gone down from 2,520 possible ways of picking to 360 ways of picking. So that's the picking all or pick sum, the arrange all or arrange sum. Now let's look at combinations. Keywords. When you walk out of that shop with 3 books, it doesn't actually make any difference to you which one you had chosen to begin with. See, which one you chose first, which one you chose second or third. Because walking out of the shop, you had the 3, and that's all that matters. You don't go home and think, I chose this one first. It doesn't matter. All that matters to you is you've got the 3 books that you saw and that you wanted. So order doesn't matter. The example that's being given here, if we have these letters, and we're to choose two of these letters, what possibilities do we have? What we'll do is we'll fix the first one. A could be chosen along with B, A could be chosen along with C, A could be chosen along with D, and A could be chosen along with E. There's really no other ways of choosing two from these five that has an A in it. So now we'll say, okay, B. Now we can't choose B along with A because that's the same as choosing A along with B. Walking out of the shop with those two books is the same. So we're saying, okay, it can't be with A, so we'll have it with the C. And we're now saying B could also have been bought with the D, or B could have been bought with the E. There's really no other ways of dealing and forcing it with the B. So now we're saying, what if I'm going to choose C? I'm going to say, choose C along with A, and you say, oh, hang on, that's up here already. Choose C along with B, that's there already. So we get to choose C along with D, and choose C along with E. And there's really no other possibilities. So now we're saying, let's force and buy D as one of the books, and we'll say, D along with A is up here already. D along with B is here already, and D along with C is here already. So D along with E is the only possibility. That's them all. Combinations, which has to do with choosing or selecting. What's the equation? And we will show how it's arrived in a few seconds. It's n factorial divided by. Now I'm going to just switch the order at the bottom in comparison to how it's normally put in the books, and I'm doing it so that you'll be able to tie it back to what you've done already. So how could we interpret this? Okay, you will remember that bit. When we were picking our items from n, that was the amount of possibilities that we had. You'll notice that we're now dividing by what could be quite a large number, which means we expect to get smaller numbers from the combinations than we would in permutations, because in combinations the order does not matter. In permutations, because the order does matter, it means that AB is not the same as BA, so you expect to have more possibilities. Okay. In mathematics, when we don't know what the answer is, we give it a name. So we're just saying, well, the actual number of ways of choosing R from n we'll call x. So what do we understand about this? Well, he's going back to the arrangements formula. This is the pick formula. By this formula, each of these x So he's saying, of these, if you pick any one of these x ways, we'll just say the third way. There's R items in there. And we could start to arrange those R items. And we'll get factorial R ways of arranging them. That's all he's saying here. So now, we're saying x, which is the number we have up here, by R factorial. He's saying is n factorial all over n minus R factorial. That's us going back to the stuff we just learned a little while ago, the arrangement stuff. Because it's actually easier to think in terms of arrangements than thinking in terms of choosing. And we have a very valid expression here. That's what we know already and what we were able to deduce in relation to picking. And we're saying that number is going to be exactly the same as the number of ways of choosing our items multiplied by the number of ways of arranging the items, the R items, in each one of those ways. So we're saying every one of these x, inside in it we could have arranged the items R factorial ways. So now we're able to say that implies x is equal to, and now we get the formula that we saw before. And as I've mentioned, I prefer to write it this way, even though the books will normally put that ahead of this guy. This isn't particularly hard. What you can see from this over here is if I bring that down here, I'll say, that's equal to NPR divided by R factorial. There's a few little things you need to understand. This is what we're calling NCR, which is NR. Now, there are three you need to understand. N0. What's that saying to us? How many ways is there? And the last one, the last thing to learn in relation to these little helpful things, in, oops, that the NCR is the exact same as n minus r. Believe it or not, this is very useful because it'll cut down a lot of calculations. And the secret to it is that and that. One could be in the front and one could be at the back. We're saying if I choose r items, I want to have n minus r left over. And what we have here is we have factorial n on top divided by the factorial of the remainder by the factorial of the amount chosen. And you'd say, what if instead of choosing r, I'm going to choose n minus r of them? Well, you'll finish up with n minus r underneath and r underneath. Sorry about this. So, by just considering this equation here, we can actually understand this one. But it's important to remember this one, because if you remember this, down here, you cut back on the amount of work that you need to do. And I've always found that a very strong motivator. For example, choosing 8 from 11. Gives me the exact same answer as choosing the 3 from 11. It's time for examples. Remember, the wording is very important here in this section. So let's read what the problem is. In how many ways can a subcommittee of 4 be chosen from a committee of 9? That's the first question. Second is, in how many ways can the subcommittee be chosen if the chairperson of the subcommittee must be, or of the committee must be on the subcommittee? That's bringing in a restriction, of course. We want to choose 4 from. Now, this is important because it will show you again something similar to what we found for the permutations, that these could the subcommittee. That's a restriction. When you deal with the restriction, you always look to it first. So in this part 2, now say, consider first. We don't have a choice here. Chairman demands to be on the subcommittee. Now, what we're looking at, we choosing 3 from 8. So what we get is 8, 3, multiplied by, which is we're choosing 3 from 8 and putting the chairman on. There's only one way of putting the chairman on. So we get this, and you will get that it's in total, it's 8 by 7 by 6, 1 over 3 by 2 by 1, for the exact same reasons as we found this thing came out from this big one. Cancellation. That by 1, which is equal to in total 56. But don't forget that we still have to put the chairman on. So his is the 1 multiplied by 1, the and 1 chairman. So that one restriction has cut down the amount of ways of choosing members for this committee from 126 down to 56. So what have we discovered in this? We had this, just showing it by its 2 methods, or its 2 styles of writing it here. And we were saying, well, it is n factorial all over n minus r factorial by r factorial. Let's flesh that out a bit. And we will make our way all the way down to and we will just leave it like this, and that gets multiplied by so in the exact same manner as we saw in the P equation, we have the same thing here for the C equation. So how far down did we get on the top line? We got from n to n minus 1 to n minus 2, all the way down to just 1 bigger than the R location. That's one way of doing it. Here's the other way of doing this. The trick is, which is going to be the easiest to use? All you can see is we've just played with numbers. And now we're going to look at the second way of addressing the problem. Okay, let's start the game again. And we're going to bring it all, we're now going to focus on this one rather than on that one. So we're going to go how far down? we're going to go to this one, n minus r plus 1. And we're going to look at the n minus r, and all the way along down to 3 by 2 by 1. And now we'll expand out this one. Sorry. We're now going to leave that bit. We're going to leave this guy. We put it here. And we're going to expand out this guy. So we have it multiplied by n minus r in the books, and it's very often, quite an easy one to use. But sometimes, depending on the numbers, how many you're choosing from, and how many are being chosen, sometimes that can give you the shortest answer. This is the one you normally see, though. It's much of a muchness. It should make sense to you. The one that gives you the least amount of multiplication is the one you should pick. Now, in B, we've basically gotten through the permutations, how to pick things, either all or some, and choosing or selecting. We've also an understanding of something and something else and something else. We should understand something or something else, or a third thing. And we understand at this stage that if there's any restriction imposed, that we look at the restriction first and foremost. What other key little things are required for this particular chapter? This one, which it crops up in 2 or 3 guises as you move on through the chapter, but fundamentally the idea remains the same. If we're asked things such as at least, in other words, this is the phrase. Those two. And later on, we will find It took me a little time to find that it is further on in the chapter. When we get these type of expressions, what it's basically saying to us is that we would have to check through all of the different possibilities, and sometimes that could entail a lot of work. So there's this little game we can play, and that's why this gets an NV. We don't actually do it. What we do is we look at the opposite to what we're asked. Sometimes when they'd say at least so many things, you could have a lot of calculations to do. So you look at the opposite of this situation, having looked at all the possibilities first, all that we're going to choose, then we look at the one that's opposite to the phrase. And if I take one from the other, it must mean the at least or the most or the phrase that we were asked. Now, rather than trying to give you a very clear understanding in English of this, which may just confuse you more, the easiest thing would be to look at a problem. Example. We have this word, sectional. First question is, how many choices of 2 vowels and 3 consonants? Okay. Two vowels and 3 consonants. Notice the operative word and here means that we're going to be dealing with a multiply. How many of them are possible? Well, we know there's 9 letters. 4 of them are vowels. 5 consonants. So this piece of the problem is easy. We write out our problem. And this is the secret to this chapter. You always write out carefully in language what you're dealing with, okay? In the first part here, we're saying we're going to choose 2 from 4 and going to choose 3 from 5. Or put the other way. Once we've said and, that means multiply. So we're finding that it's 6 by 10, which is 60 ways of choosing 2 vowels and 3 consonants. Okay. That bit's the same as we've done so far. Part 2. How many arrangements of 2 vowels and 3 consonants are possible? This is choosing. Okay. Okay? The second one, they're asking us how many arrangements. That's the key word. Three vowels, two vowels, three consonants. And means multiply. Now, there's two ways of looking at this. We're looking at arrangements. We could say that we're going to look at 4p2 multiplied by 5p3. That's one way. You could always, and that'll give you an answer, of course, the right answer. The other one is, well, we already know that we have 60 ways of choosing 2 vowels and 3 consonants. And now the difference between choosing and arranging is that each of those sets can now get arrangements. We can find how many ways we can organize them, okay? So we could, instead of that, we could say, this is the same thing as saying choose and arrange them. So we already had 60 multiplied. We're using multiply because it's and. So then, isn't it interesting how when the order doesn't matter, we've a choice of 60. When the order does matter, it blows up to 7,200. Well, that's still not too difficult to work out. So what could get more difficult? Let's look at the third part of the problem. How many choices of 4 letters, including, this is the thing, at least. Okay, this is the phrase we're going to be dealing with. 4 letters. Okay. So how many of 4 letters that include at least one vowel can be made? Well, that's a particular problem now, isn't it? Because at least one vowel means that it could have 1 vowel, 2 vowels, 3 vowels, or 4 vowels. And you'd have to do lots of calculations. but we have a shortcut. And the shortcut is to do the complete opposite to this. At least one. What's the opposite? So, how many choices? Okay. That's the total number of choices, picking all the letters of our word, okay, which is sectional, 9 letters. That's why we have our 9 up here. That's the absolute total number. Now, if none of them are a vowel, then there's only this many choices. Because now I only have 5 consonants to choose from. I'm not allowed to pick a vowel, and I'm still picking 4. And this gives me an answer 5. If I take one away from the other, I get 121. What we're saying here is the way of picking 4 with absolutely no restriction at all from the 9 gives us 126 choices. If I impose a rule that there'll be no vowel, I'm now picking 4 from 5, and that gives me 5 choices. If we examine that condition, 5 consonants, you must pick from 5 consonants. That's the same as not picking any vowel. So, unrestricted, no vowel. The difference between the two of them must be at least one vowel. So 121 possibilities has at least one vowel. And we've saved ourselves a lot of work doing this. The wording of the chapter now begins to change. These same little games that we're playing isn't changing at all. But we're now going to start talking in terms of probability. We're going to bring in nice new words, an event. And what is an event? It's an outcome or a group of outcomes. We're talking about the chance of something. When we perform a test. So then, we have an event, which is an outcome or a group of outcomes. And we're wondering what's the probability or the chance that a particular event occurs when we perform a test. And what we'll find is the probability of this event, and a bit like we go f of x, and we use the letter f because it's the first letter of function. We're just going to use e here because it's the first letter of event. The probability of the event is equal to r 1 over n. And what is that? It's the number Now then, we need one new word, experiment. The experiment will tell us the total number of outcomes. It's the game that gets played. In the game that gets played, there'll be a number of events that'll be of interest to us. For example, a six-sided dice. We might be curious to find out how often would the number 2 turn up. So there's 6 possibilities, 1 up to 6. So the experiment has a range from 1 up to 6. Now, all we have to do, and it's a very important aspect of this, is we have to be very careful to ensure that we know what our event is. And having defined what our event is, we then we need to know what our experiment is. And having defined that, we then need to look at the particular events that are of interest to us, okay? So, this equation here tells us one other thing. It also tells us that the maximum probability something can have. In other words, if R is as big as n itself, then P of E is 1. So our numbers that we expect to get out of this, our probability values, will range from 0 to 1. At random means that this is not biased. We are not secretly looking at them and deliberately picking out a king, for argument's sake. We don't know what it's going to be. It's a blind draw. Yes. There are important words that start to come in now. Instead of just talking about a pack of 52 cards, we will use the word standard. Because one of the things you have to be sure of is, okay, you count the cards and there's 52 of them, but maybe somebody has put in 20 kings in there. So the word standard tells us it's the same as the type of pack that you would buy in a store. And you take away the jokers and any other card like that, and you've got all your usual cards. That's your standard pack. Okay? If we're looking at a dice, a 6-sided dice, you would look for an unbiased 6-sided dice. In the old days, there were people who made a lot of money out of having a weighted dice where they might have put a bit of lead in on one side, knowing that when you throw it in the air, that the lead side being heavier is most likely to be the side that will be in the bottom. And if you were looking to win sixes, it was the number across from 6 that you would hide the lead in. That's an unfair dice. You will not get an even chance of each of the 6 numbers turning up. The one that's across from, on the opposite face from the one with all the lead in it, is going to be the one that will show up more often. So we're going now dice, or sorry, standard packs of cards and unbiased dice, that kind of thing. And we're just simply using these words so that you know that you don't have to think outside the box on these problems. So here's the obvious type of things. What's the chance of pulling a 7 from this pack? We know there are 4 7s, okay? Here's the experiment first off. Choose a card. Remember the operative word choose. How many possible ways? N is 52. There's 52 possible answers, isn't there? So we've established what our experiment is. Here's the first question that's asked of us. The event. And we're looking for get a 7. How many 7s are there? There are 4 7s. So R is 4. So then P of this event that we're talking about here is 4 over 52, which is equal to 1 over 13. Couldn't call that difficult. So what are we going to do now? The second time is we want to see what's the probability of an ace or a king. Now let's look at our words again. An ace or a king. That's a plus scenario. 4 aces, 4 kings. So R is equal to 4. R equals 4. The plus comes in because of the R. It's an ace or a king, because it can't be an ace and a king. We're only picking one card, and the card can only be a single individual item, so it can either be an ace, is what we're looking for, or a king. So that's why we have our plus down here. You'll notice the same rules of language are applying even now 2/3 of the way through this chapter. So what's the third thing? The third one, and to try and make this a little bit more complicated, is to bring in another little lesson that you have to learn about now that you're dealing with probability. And as well as recognizing our friend R in here, which is going to tell us that we'll have a plus, you now have to recognize something else. And it's why you always have to be very calm, very clear in your mind when you're doing these probability type of questions. There's 4 aces, definitely. Okay? Just write it over here. So R is equal to 4. There are 13 diamonds. So is the R for this or a diamond business, is the R going to be 13? It can't be. And the reason it can't be is we could finish up double counting. If we're picking out an ace, and if the ace turned out to be the ace of diamonds, well, now you're saying to yourself, that's accounted for one of the diamonds. So what we have is we have an overlap between one of the aces and one of the diamonds. And what you have to learn from this third part of the problem is we're going to say that because these are not independent, these two things here, not independent, we'll say fully. Not fully independent. We have to change the game into an independent one. And how we do it is we change the request. The request will get changed to choose an ace or a different diamond. We're bringing in this word so that the choosing of an ace is now independent of the other option, the R bit. So how many different diamonds are there? 13 diamonds, yes. But 12 different diamonds. So R is 12. Now what we're going to get is we have 4 over 52 well, actually, let's try it a little bit different. R means plus. A different diamond is 12. We're still playing the same games. We're being very careful with our language. We're looking to choose something or something else. That's a plus. But now, when we're dealing with probabilities, in the same ways we're now using nice words like standard pack or unbiased dice, we're also needing to be careful that we don't get an overlap. We want full independence. To do that, as you can see here, sometimes we need to bring in one new word, which is independent. Here's another example. One disc is drawn. What is the probability that it is green? Very simple looking problem. It's only in here to clarify one issue. If you were to actually examine the 4 red discs, they would look absolutely identical to you. Same size, same shape. And likewise, if you looked at the 5 green discs, they would look the same as each other. And we will just take it that they're identical. So we have 4 identical red discs, 5 identical green discs. But those identical red discs aren't one disc. They're separate. You can sit them together and you can count them up to 4, which doesn't take too much effort. So we're saying, when we're working out the experiment, we're looking at the total number of possible events. And we could choose from how many? 9. Even though some items may be identical to other items, they all count in their own right. So there's 9 items here, even though 4 of them are identical and red, 5 of them are identical and green. So event to choose a green disk. Probability of the event is 5/9. Don't dismiss this simple problem because it was deliberately put into this book so that you do not make the mistake of considering identical items as just being one item. They're not. They're separate. When we're looking at possibilities, outcomes, if the numbers aren't too big, well, then we can actually exhaust out the experiment. We can work out all the possibilities. In other cases, we can't do it. It often doesn't take too much, actually, to exhaust them. For example, an unbiased die as it dies. See that word coming in? Like a standard pack of cards, an unbiased die. They're very important words. Otherwise, the probabilities that we'll be talking about will have a skew and unfair, and it'll have a bias. Now, what we're told here is First question. What's the probability of getting an even number or a red one? Or will imply plus. What we have to work out now is there an overlap between the two things? This on the left hand side and this on the right hand side of my R. Is there an overlap here? Well, even number. Where are they? Two of the even numbers are coloured black, but one of them is a red. That means we do have an overlap here. We're going to replace our system with okay. Now we could do that by exhaustion. We could easily work out the possibilities. Experiment. One throw in its 6 event. We're going to look at this. What is it? A different red one. We cannot put in the 4 over here because it's counted in here. So we're saying R is equal to 3 plus 2, which is equal to 5. Now let's look at the second half of the question, where obviously we'll get a somewhat harder problem. The die is thrown twice. What is the probability that a total of at least 8 is obtained? Now obviously we could do what we've been taught so far, but this is your opportunity to work out the answer through exhaustion. And that isn't your exhaustion, of course. So it's thrown twice. What is the probability that a total of at least 8 is obtained? This has nothing to do with reds. It has nothing to do with colours. It's just got to do with numbers. We have 6 numbers. It's going to get thrown twice. When we talk about the total, we're saying, let's assume 6 turned the first time and 2 turned the second time. 6 and 2 is 8, so that's a total of 8. So let's set up our game. So now we're just going to start adding. 1 and 1 will give us a 2, 1 and 2 gives us 3, 2 and 1 gives us 3, 2 and 2 is 4, we could say this is the first throw and that this is the second. So if we in the first throw got a 4 and in the second throw got a 5, we're saying that the total is 9. And the question we've been asked, what's the probability that a total of at least 8 is obtained? Well, this is going to be easy. Now notice this is an at least problem. If we do it by exhaustion, we don't have to worry too much about that at least situation. So what we're saying here is I can count up all of these. 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 1, 2, and 1. Okay? So we're saying there's 15 of these. Okay? How many total squares do we have? The experiment ends when we have 36 squares. The event E, R, is 15. Probability of the event is equal to 15 over 36, which is equal to 5 over 12. If we had been asked what is the probability of at least 8 and no more than 10, if we were asked that question, well, we're now looking between this red line limit and the blue line limit. Instead of R being 15 now, because we're looking for at least 8 and no more than 10, R will be 12, and it'll be 12 over 36, which will be a third of the possibilities. So you can see how in many of these cases you can actually work through all of the possibilities and exhaust the situation. There's just 2 last sections to this chapter. Multi-stage probability is the second last one. What do we mean by multi-stage? do one thing and do another. It's a multiply. What you've already done in relation to probability, you can see as being this particular event. What you've done already in probability, you could see as being that. And all we're looking at now is the exact same thing that we started our chapter with, which is something and something is a multiply. This is just simply showing you how the little tools that we have now are getting combined in different ways to allow us to deal with more complex problems. And remember, a complex problem isn't a difficult problem. It's just got a lot of little bits in it. And the real secret in mathematics, and particularly in this chapter, is to never step away from the most basic little rules. And is multiply, or is add. If you have a restriction, you look at it first. Things have to be independent. If they aren't independent, you can push in a word, you can change the game by putting in the word different, as in the ace or a diamond becomes an ace or a different diamond. That's all that we have in these particular things here. Now, let's look at one of these little things. A simple example should suffice on this. Felon So the letters of this word felon are arranged at random in order. Now you'll notice our learnt words arranged is coming in here, and now we're bringing in the words like random because they're kind of words associated with the probability bit. But this should be easy enough. This is the first little bit here. Saying what is the probability that the two vowels are not side by side? Okay. So what's the possibility of that? Okay. What's the experiment? "120 ways of arranging the 5 letters." Okay. Now we're looking at the particular event or events that we want. Okay. The one thing that I haven't discussed as we went along in this discussion on probability has to do with when we can combine or tie things together. It comes in several times in the chapter, but now it's probably better to cover it now, because what I've been trying to do so far is to just explain those basic words and how things build up and the relationships between permutations, and then across to choosing, and now moving up into probability. So we're saying E not next to O. How many possible ways? This is one of those, like at least, at most problems that can be quite difficult because there's so many ways of doing this. So what you do is you set that aside and you take the opposite of it. And you'd say the opposite is that they are side by side. Once you say that they are side by side, that's a restriction. What does the restriction mean? It basically means that we now have these two welded together, stuck together, glued together, whatever way you want to think of it, okay? These two letters are now going to be stuck together. So instead of 5 letters, we now have 4 letters, one of them, or sorry, 4 objects, one of them being a bit odd because it's a stuck together 2 letters. So that should be easy enough to work out. Now what we will get, sorry, I actually go to the second half of it. But here's the problem. In sticking them together, couldn't I put the E first and the O first, or I could have gone O, E. EO is not the same as OE. So if I've glued E and O together, I can look at the amount of ways of arranging these 4 symbols, the F, the L, the N, and the EO symbol. I'll also need to look at the F, the L, and the N, and the OE symbol. We can look at that by saying they're glued together. That's the restriction. We'll start with that. And then we'll say, inside the restricted group, how many ways could I actually pick those? How many ways can I organize those? So we will do it like that. Arrange 4 by arrange 2. The arrange 4 are the F, the L, the O, and the EO combination. The arrange 2 recognizes the fact that EO, those two things could have been glued with the E in front of the O or the O in front of the E, so we're just looking at those arrangements inside in the little group here. So what answers do we get from this? We found that there are 48 ways that we could actually arrange the characters L, N with the EO combined in some order. We also had found that there was 120 ways of arranging the 5 letters without any restriction. Probability of the event that we were asked. And you can see the event, it's written here, where E is not next to O. It must be equal to the unrestricted condition minus the opposite restriction. We have those, and all that is now going to be divided by the total number, which is 120. And the answer is 3/5. So above the line, we have 120 minus 48 to give us the actual number where E is not next to O. It's getting divided by the total number with no restrictions, which is 120, and we'll get the probability of E not being next to O is 3 over 5. So it's 0.6. The exact same thing can be done in this multi-stage probability as we did in the last exhaustion problem. We can actually exhaust out the possibilities in some of the problems where we can tie things together. And for example, you just can finish up with either a long list or, as I did in the last one, come up with a table. And you will get all of the possibilities, and then it's a simple counting game. And count divided by the total gives us the probability of the event that we're looking at. There is a very interesting comment that's been made by Rowntree in his book now. It's very close to the end of this chapter. He's saying two little points, actually. They're related. If you see the phrase in succession, he's saying order is involved. He's telling us that it's like items on a mantelpiece. We're looking at them, and the order that they're in does matter. These things are in succession. So that phrase here should be triggering that we would be looking at an NPR type of situation rather than an NCR type of situation. The second half of this is the word pick, obviously. Now, he's now breaking one of my little rules, and that's why I'm mentioning this to you. He's saying the word pick indicates that the question can be dealt with either by arrangements or combinations. Now, I normally use the word pick to deal with arrangements because, first off, NPR is like from N pick R. It's an easy way to remember it. The other thing is, here, in discussing this, he's stating that there is an ambiguity. Now, what he goes on to say is that although he says the combinations are often the more straightforward way, but the issue is, if you've got ambiguity, if a question is asked and you're not certain, and it's the word pick that he's talking about, this one here, you can choose one or the other. You can choose to go permutations or combinations. The only important thing really in relation to it is, remember your exam paper, your answers. They're a communication document. If you make a decision, write down what your decision is. State, I am taking the word pick to mean, and you choose the one, or you write in the one that you are going to follow. Because if you don't do that, you're leaving yourself open to be misunderstood. And it would be ridiculous to lose marks for being misunderstood.
There's one remaining section that we have to cover. It's very simple. You will actually find that you've already heard everything that's in this, but it's just going to be presented a little bit differently. For example, when we had a situation of picking a heart from a deck of cards, you knew how many hearts were in the deck of cards, and you would be able to say to yourself, okay, what I actually have is the total number of hearts as the possible number of outcomes that will be successful, and 52 being the total number of cards as being what they're getting picked from. We're going to talk about it now in terms of the probability of doing things and how we can combine probabilities of successive events. And there's just one little trick that you have to be aware of before you can look at your problems in this particular fashion. Now, fundamentally, what we're going to talk about is the multiplication law. The multiplication law of probability. And it's basically written as this: if A and B are independent events. That is really important. They have to be independent events. We can say the probability of A and B occurring is equal to the probability of A occurring multiplied by the probability of B occurring. It's critical that they're independent, because if they're not independent, this doesn't hold. Now, in a lot of cases that we're going to be applying this, B is actually dependent on A. So what we need to do is to find a means of changing this around so that we can use it for all of those type of events. And what we do to adapt the law is we change what we mean by this. Probability of B is going to be probability of B after A. For example, picking the cards that I mentioned to you, there are 13 hearts in the 52 cards. If we were looking at the probability of getting 2 hearts, the first option, the A one that we're looking at here, is getting any one of those 13. So we can say the probability of A is 13 over 52, which is 1 in 4. What's the P of B? Probability of B. Well, we're saying given that A has occurred. Well, there aren't 13 of them in there anymore. There's only 12 of them. So the probability of a heart and another heart is equal to the probability of the first one by probability of B after A. And we can say it's 1 over 4 by 4 over 17. So even though we're using this law, which in its pure state is saying to us that A and B are independent, we're able to adapt it by redefining B. The probability of B is the probability of B after A. Obviously, if we have our 52 cards and we're saying what's the probability of getting a heart, and then haven't picked a first card, you return it to the pack. The second time around there's still 52 in there. So the probability of getting drawing a second heart would be the same as having drawn the first heart. It would be 13 out of 52. In that case, both A and B are fully independent. But here, because when you've pulled a card, the A card, you don't return it. So the B event is dependent on it. Now, basically, it's not that you will get a particular part in the Leaving Cert question which will be must be answered like this. What you're looking at is an alternative way of doing something, and the best way of looking at that is by giving an example, and it's straight out of Rowan Tree's book. 2 fair coins. The important word is fair. Remember, I've mentioned to you certain words now start to come in that you wouldn't have had in the early stages of the chapter. You need a fair coin. You will have properly balanced dice. You'll have a fair dice. So these words are important. They are indicating to you that you can correctly distribute your probabilities. So we've this, and we will have a bag containing three red and two white discs. So that's the hardware. You need 2 fair coins and a bag with 5 discs in it, 3 of which are red, 2 are white. What's the question? What is the probability? Getting 2 heads and a white disc. Again, I'm putting in capitals as I have all the way through this section. The important keywords like and, okay, because and, as you know, means multiply. Getting a first head and getting a second head and a white disc. So all of these things will multiply. Well, in a fair coin, there's an equal chance of getting a head or a tail. So it's 1 and 2. Same with the second fair coin. And now we're saying there were 2 white discs in total in a bag that has 5. So when you multiply that out, you get 1/10 chance that you will get 2 heads and a white disc. What's the alternative method? We're setting up an experiment. First coin and second coin and a disc. The experiment is we're going to toss a coin, then we'll toss the second coin, and then we'll pull a disc. And any possible outcome of that forms the experiment. And what we will look for is the amount of outcomes of this experiment that will fulfill our objective, the particular thing we're looking for. So, n, what's the number? 2 possibilities here. That's a multiply. 2 possibilities here. That's a multiply. And there's 5 discs there. Total of 20 of these possibilities. What's the event? We want a head and there's 1 chance out of 2 in getting ahead from the first coin. There's 1 chance out of 2 getting ahead from the second coin, and we've got 2 out of 5 chances of getting the white coin. So there's 2 chances there that'll actually fulfill our requirement for white. And you'd say, that's a total of 2. So that implies that the probability of this event, E, is equal to the 2 over 20. That's just that number divided by that number. So you'll see we get the same answer here as we did up here. You now have 2 different ways of looking at it, and my attitude is whichever one suits your mind is the best one, because at the end of the day, one of the main things you're supposed to gain from mathematics is a strengthening of your ability to apply your own style of reasoning to things. One last example and we'll finish on this. We want to introduce a new concept. Did you notice there, out of 20 possibilities, 2 of them would have given us a head, followed by a head from the second coin, and a white disc, and 20 possibilities was the total. So there was 18 chances that you wouldn't get it. So let's define something. The possibility of success, or probability of success. It's equal to 1 minus the probability of failure. In our last example, we had 1 over 10, which we know is 0.1, and we're saying, that's 1 minus, and we know the probability of failure then had to be the 0.9. For the 3rd time in this chapter, we're now going to look at the type of problem that normally gives people headaches, and the exact same approach is going to be applied to save you that headache. It's the situation where you have got words such as at least, at most, those are the kind of words. And this is often a way of finding the shorter way of solving the problem. We'll pick an example. Four people chosen at random. Another one of those nice words that comes in now that we're dealing with probability and the options of things. Chosen at random. In other words, just because one is chosen, that's not going to in any way interfere with the choices of the others. Purely random. And chosen from a group, 6 men and 8 women. Here's the question. Notice the term at least 2 men. Okay. First thing we do in our experiment, we just look at choosing, without any sort of restriction whatsoever, 4 people from the total group of 6 plus 8. So we're saying choose That is N 14, 4. 1001 possibilities of choosing 4 people from 14. Okay, so what is success here? That, as you can see, is using this word up here. What are we going to define as being success for us? At least 2 men. So we can now define failure. And now we have to decide which is going to be the easier path to do, to drive straight just to find what's our successful outcomes, or will it be easier to look at the failure ones and take the answer, probability answer of that away from 1. So in failure, what are the possibilities of getting less than 2 men? You could get no men or 1 man. Notice the word again. Or means plus. So whatever answer we get from this, we're going to add to the 1 man option. Now, how many possibilities are there of getting at least 2 men? 2, 3. I'll write it the longer way. So we've got 3 cases to look at here, whereas in this one over here you only have 2 cases. It will be easier for us to look at this side. Now 3 versus 2 isn't a huge difference, but in many cases the difference can be massive. So how can you get 0 men? This one here is 4 women and this one here is 1 man and 3 women. And you'll notice in between them there's an or. So we're saying this is a plus and the and is a multiply. These are our options. So 4 women, that would be out of 8 people. You see our plus here. And now over here we're saying 1 man is out of 6 people, we're only going to get 1. And we're going to multiply that by getting 3 women out of 8. So that's easy. We can say then the probability of failure is equal to total number of possibilities is 406, and they're being divided by, sorry, possibilities of failing, and they're being divided by the absolute total number of possibilities which we had worked out up here in the experiment. Of getting 4 people from 14, there's only 1001 ways, and of those 406 of the ways would give you a failure that's no men or just 1 man. So now we can say this P of failure implies P success equal to 1 minus P failure, which is equal to 1 minus and that's 85 over 143. So our success is 1, probability of success is 1 minus the probability of failure. So we get 85 over 143 as an answer. That's easy stuff. The other thing that's nice about it is this is the exact same process that you will have seen for the 2 previous times that we've encountered words such as at least, at most, less than, more than, or no numbers of things. Where there's quite a number of possibilities, trying to hunt the one you're asked for can often be harder than finding the opposite. And that's what this is telling us here. It's an interesting chapter because as you get through this chapter and as you get familiar with ideas, it actually gets much easier. And this last piece here is just sensible, and it shouldn't cause any undue worry to you, because once you have the ideas and you do understand, you're either going to be successful or not successful in something, and the total probability is 1, so the probability of success is 1 minus probability of failure. That is also sensible. Okay, that's the end of that chapter, and I'll see you the next time.